Thank you, Kami. So good morning. My name is Björn Reineking, and I'm based at INRAE in Grenoble. INRAE is the French National Institute for Agriculture, Food and Environment. And in Grenoble, I'm working in a research unit called LESSEM, where we're interested in ecosystems and societies that are situated in mountains. So we have a group of sociologists, economists, ecologists, many of them working in either grasslands or forests. And one of the things that I'm interested in, for example, together with Alice, we are looking at how certain species, in our case, black grouse, react to human activities in the mountains. So what happens in ski resorts. And for that, we link, or we use tracking data. And that is one of the examples of how you can link tracking data, so movement, and environmental conditions. In our case, it's descriptions of human activities, but it can be, as Kami mentioned, anything of these remote sensing data that we looked at yesterday. And this is what I'd like to discuss with you today. Two ways of linking movement and environment. There's, on the one hand, resource selection, which is very close to what you might have seen as species distribution modeling or habitat modeling before. And then there's step selection function, which is a way of integrating more of the actual movement process. And what I'd love to do is, when we do this here, that it becomes as interactive as possible. Okay, so I'll ask you sometimes questions, but please do interrupt me at any moment. So why should we be interested, or could we be interested in linking environment and movement? And I see that there are two big groups. The first one is predicting what happens in the future, either under current environmental conditions or when they change. So if you build a road, what might happen? If we change activity patterns, what might happen? If you clear the forest, what might happen? And there are two parts of the animal trajectories in the future that we could be interested in: the utilization distribution or the range distribution. So where is the animal in the long run? And then we could also be interested in how specific movement paths are changing. And that is something, this movement path is something we can deal with step selection function. The utilization distribution we can do with both approaches. And then the other part is understanding what drives the species, what drives the animal. And on the one hand, different aspects of the environment. This could be the resources, that could be risks, that could be just general environmental conditions, such as temperature, how they shape the movement path, and as resulting from that, the distribution of space in the long term. And we can also make this a function of characteristics of the individual. So how big it is, what sex it has, what it eats, and so on. And then another aspect that can be interesting is to quantify the effect of drivers. This would be, in our case, well, if we have more or less tourism pressure in the Alps, how will that translate into space use? So I'd like to start with contrasting RSF and SSF, and then we'll zoom into RSF, discuss how that works. Then I suggest we do a session, an R session on RSF. Then we come back, discuss how SSF work, and we go into SSF analysis. Okay, that's sort of the big outline of today. So what's the common thing and what's the difference between RSF and SSF? And I like to think of both of them in a way as aiming to predict where the animal will be. And they differ mostly in what quantity they predict. When we have an RSF, so here, to situate ourselves, this is Scylla, this is the buffalo that we all know and love, overlaid on elevation. And one thing that we could be interested in is, where is Scylla in the long run? you've already learned at least one method of doing this. This would be AKDE. Yeah, AKDE gives us the same this range distribution. And what is now different to AKDE, we want to express where the animal will be in the long run as a function of the environment. AKDE tells us where we can expect it to be, just looking at the places where we've observed it, and now we want to express where it will be as a function of the environment. Okay. In contrast, SSF takes a more short-term view. Again, we want to predict where the animal will be, but only where it will be in 3 hours from now. And we condition on the animal being at a given point. So here we have zoomed into this whole data set a small part of the trajectory of Scylla. It came from here, moved here, and now the question is, where can I find it in 3 hours from now? It actually moved here, but what's the probability that it could have moved there, or there, or there? So again, we want to have a model that tells us for any place on Earth, essentially, where it could be 3 hours from now. And this would be then a prediction here where red is giving us a high probability of being there and blue a low probability. And here again we have elevation. This is lower elevation, this is higher elevation. So it seems that the model suggests that the animal has a tendency of moving downhill. Okay. So these are in a way, there are two things to take home from this. In both these approaches, we try to predict where the animal will be in the future. In one case, in the long term. And here, one step in the future, just the duration that we decided. So yeah.
So with RSF, I mean, it seems a bit of a stretch, but can it be used to transfer models of range distributions from now to the future with, let's say, climate change variables?
In theory, it's meant to be able to transfer in the future. Climate change is a tricky thing because normally you don't get, by observing a trajectory of the animal now for a short period, you don't really have the response of the animal to the climate. You see it perhaps how it reacts to local temperatures, but it's a bit of a stretch to say that this is then what's going to happen under climate change. I think it's easier to see, well, if you have something that is more localized, like habitat structure. If you change the habitat structure, what will happen? Yes, then that's easier to do. We'll come back later to the question of scale, spatial scale at which we analyze the data. I'd say if you have many animals over a large environmental gradient, and you assume that you have sampled this environmental gradient properly with your species, then you can create models at the level of the distribution of the species, and with the assumption that the current distribution of the species reflects mostly its response to climate, and that this response will stay the same in the future, then you can also predict what happens under climate change.
Thank you.
So we will mostly focus here on the more local scale, and their climate is difficult to integrate, but it's not impossible.
I was just, I guess, meaning on like a consequence of climate. Well, it is climate change. So sea level rise, it gets habitat that was available, but in the future is predicted to not be available. So it's at the local scale.
Yeah,
yeah.
That should be. That's easier to integrate. So this is, in a bird's eye view, what's the difference between what they predict and now what are the assumptions that underlie these methods. And now you know what these sentences mean. So here this says it assumes that positions are statistically independent. Yeah? So that's what we'd seen earlier. So if you have your variogram, and then where we hit the asymptote, more or less, that's when the positions are independent. And then here we assume that velocities are independent. So that is, again, coming back from our variogram. I'll show this in a minute. So when we leave this initial quadratic part and we enter the linear part. And these assumptions are important because if we don't meet them, then we might get completely wrong estimates, in particular estimates of the uncertainty. The cool thing about step selection functions and relative to RSF is that we can simulate future trajectories. So we can not only say where it might be in the future, but also what might be likely path to get there. The drawback is that if we're interested in what happens at the home range scale, it's much more difficult to get these estimates because in general you have to simulate. But another advantage is that because we only need the velocities to be independent and not the whole positions, we can make more efficient use of the data. So here we often get things significant, how environment affects movement, that we wouldn't see on an RSF scale. Yes?
Sorry, I just have a question about terminology because you mentioned the AKDE and now you're using the occurrence distribution. And I just
Did I say occurrence? Oh, that's completely wrong.
Okay.
That's completely very good catch.
Okay, thank you.
I fixed it in one place. No, this is not the occurrence. It's the range distribution. Or some people still use utilization distribution for range distribution, but occurrence, that's definitely wrong. Thank you.
So range distribution and utilization distribution are synonymous? And
At least when I use it here, okay. And you'll see it used synonymously in other papers.
Okay, thank you.
But occurrence, that's completely wrong. Completely wrong. Yes, thank you. So now the question is, what determines the range distribution? This is the Scylla observation. This is our, let's assume it's the only environmental layer that affects what the animal is doing. And this is now the resulting model. Yeah, so this is a model of the range distribution. And how do I get here? So what are the factors that tell me this point is not very much used, this point is very much used? What would you think are factors that we should take into account?
Maybe because before we just have like a general estimation with the occurrences, like with the positions that we have, by integrating the elevation, we can have like a limitation of the range that they actually are able to use, or not.
So you were talking about elevation, and then you talked about
the positions that where they are at, and with that you can determine the range at which they can appear.
Okay, so there's some things that tell us where it'll be.
Okay. Yeah, basically, I was thinking, depending on like the information that we get from the positions, we can determine what is like the probability on the distribution of the elevation.
You're already one step ahead. You're already thinking about how can we bring these things together. And yes, we will see how we can use the positions to estimate the impact of our predictors on where it is. But now, just verbally, one could be interested in saying, well, what seemed to be driving the presence or absence of the animal in the landscape here?
Is it what's used versus what's available?
Yes.
Is it what's used versus what's available?
Yes, in a way. And what in particular, when you, so elevation here, this is the green is high and the white is low. What does the animal seem to do? When you look at the points.
I mean, yeah, just selecting specific areas.
Yeah. Did you want to say something?
I was just wondering if it's without just the points, not the tracks or the direction in which it is going. Like I can't say whether it's preferring high elevation areas or low elevation areas.
Yeah, I mean, it's if you have the direction, that would still help, but it ends up being in certain areas more often than in others. I think we and what seem to be the characteristics of the areas where it is or where it isn't.
So it appears to be at higher elevations? Is that what you're asking? Or lower elevations? Sorry.
So,
Yeah, lower
I mean,
elevations.
when we focus on this area here, what seems to be happening there?
So I have a question. Are those the raw data points?
Yes.
Okay.
Those are the GPS points.
Are they taken from a like solar GPS, GSM, or?
No, that was battery driven, and it's
Okay.
1 point every hour.
Okay. So it seems to be at lower elevations.
Yeah. So I mean, the first thing is elevation seem to be having an impact on where this thing is.
Seems to be the case.
Yeah. Okay. So we have elevation, and you say rather not the high elevation.
Yes.
I do not fully agree. I mean, why do we say that it's lower elevation? There are other areas of lower elevation that are not utilized at all. So
For
is
example?
elevation
For example,
all the path in the south?
here.
Yeah. So
Okay.
is elevation actually affecting the distribution of these animals?
What could be, I mean, if you look at this map, what could be explaining that they're not here? There's the river.
Yeah.
So, oh no. There is a river. Yeah? And it seems, apart from this point, not to cross it. And this is the very first GPS point, so it's probably an error. So, okay, we have the fact that there's a river could explain that it's not here. And this is something that's interesting to consider. How do we integrate this later on in the analysis? And here, from this, we might infer that it's not going very high. What else? So this is already, I think, pretty good with respect to elevation. What else might be happening here?
I mean, it's kind of an obvious point, but I guess the points are going to be closer to the previous points, right? I'm assuming this is a terrestrial animal, so it's not.
Yeah, it's our buffalo scylla.
For sure. So it can't jump around easily. So there's a central attraction of the points. as
So
well.
there's a central attraction. Okay. Which we could even have if it was jumping around. I mean, we had Eli talking a lot about some basic movement models, and some of them had an attraction and others didn't. And yes, I mean, if you compare a point here to a point here, which have the same color of orange, it seems that they're kind of clustered around here. So if we now want to predict the time that the animal spends somewhere, which is another way of saying what's the probability that I find it there, we have some predictors that are related to the environmental conditions at that point. That's the local elevation. And other things that are more related to general space. So is it close to the home range center or not? Yeah, so we have things that predict where the animal is because of, well, hard physical boundaries. Then there are preferences for certain habitat areas. And then there's behavioral constraints that it's not moving as fast as it can anywhere, but has a tendency also to have this home ranging. Okay. Yes, so and the aim now of the RSF is to quantify these elements. Yes, to quantify how elevation explains where it is, how we can integrate hard boundaries like rivers, and things like central tendencies. Okay. So now we look into how we can describe this thing a bit mathematically. And here is sort of the overall basic equation that describes what is the probability of finding our species or our individual at a given point in space. S is a point in space. You can think of it as one of the grid cells in the landscape. And what the probability that we find it there, given some lambda. And this lambda is a measure of how attractive or how good this place is. Okay, so this is what we want to predict. And here to the right, we see that the probability that we find it there is proportional to some lambda. And then we have to divide by this integral. Why do we have to do this? Do you see this already immediately? Not, I mean, I wouldn't expect that you see it immediately, but just in case.
Maybe because there's a centroid distribution, meaning like it needs to be within the area where we have the positions.
Yes, I mean, this is the point. It has to be somewhere, right? I mean, we know that this is a probability distribution, so it has to be somewhere. So, or if you think again of pixels, and we have this value for each pixel, then the sum of these pixels has to be 1, because it has to be somewhere. And at each pixel, the probability to find it there has to be 0 or positive. So that's why our thing 0 here, that is what is called an intensity function. That is something that is larger or equal to 0 and describes, is a measure of how likely it is to find the species there. So now this is a very abstract description of this. And the question now is, well, how do we describe lambda? How can we link lambda to our environmental conditions? And normally what we do is we describe lambda as a function of environmental predictors. So here we have h. This could be, for example, elevation. Yeah. So and the E is here for different predictors. So you could have elevation, you could have NDVI to bring in the remote sensing. So here you can think of the H are your raster layers. Okay? And then you multiply this raster layer with a parameter that tells you when it's positive, yes, the animal goes to higher values of this raster layer. So it goes to higher elevations. Or if beta is negative, then it tends to avoid them. Yeah. So this is the raster layer. You multiply the raster layer with a value that can be negative or positive. And then you stick this in an exponential function. And what the exponential function does, it makes sure that our lambda is positive. Because if you don't do the exponential, then this can go from minus infinity to plus infinity. And here with the exponential, it's something that's positive. If you're used to GLMs, and you do a Poisson regression, then you have the exponential as your link function. Yeah? And that's what's happening here as well. So here we now have our parameters that we want to estimate. Then the second, so this is in a way nice because this looks very much like regressions that we know. What is a bit nasty in a way is this integral here, because we now have to calculate this value here that we can have for each cell in landscape, and divide everything by the sum of these cell values. And there are different ways of calculating this integral. And the easiest is the one that I just described to you. You have a prediction for the whole map, and you divide by the sum of that. Yes?
I might be getting ahead, but with this equation, you are just estimating with one variable of the environment, correct? Because you just have one habitat lambda.
Yeah. E goes through all the layers.
So it is for all the, okay.
So this is for k layers, but this is just for one position. That's perhaps so then there's another, so this is what happens at this particular cell here, and then you sum over all your raster layers.
And then after, with all the different lambdas that you calculate for all the different positions, you can get the estimate for the final. Okay.
You need, in a way, you need a value everywhere to calculate this down here.
Got it. Thank you.
Yeah. So there's, in a way, there's another, for this, you have another sum that goes over all cells. This is what happens in one cell, where you sum up all your different environmental layers, and then you have a second round for the area. And this, I mean, what you just said there, this is what I wrote here. If we are now interested in calculating the integral, we can sum over all cells in the whole landscape. And then there's a second way where you just put points in the landscape. Yeah? This is when you have done SDMs, people talk about background points or pseudo-absences. Yeah? If you come across these terms, they are just another way of calculating where the animal could have been and what the attractiveness or what the intensity at that point would have been. And I'll cover this part here, the Monte Carlo part, later on for step selection function, because that's what is the natural way to calculate the integral there. Here in RSF, we often just calculate for each pixel in the landscape how attractive it is, and then sum these values up. Okay.
How do you determine the potential landscape that you use for this?
That's exactly the next point. Because that's now an important question, right? I mean, when you look at this area here, you calculate the integral over an area, and probably you get different answers when you calculate it for this part of the landscape or for everything. So yes, this becomes an important element of what we do. And particularly, traditionally, this has been a big concern. How do you define what then ecologists would call the available area? Yeah. And then in the paper by Alston et al., Chris had a good idea of how we can alleviate this problem a bit. And he alleviated it with an idea that you had also earlier. There's something like central attraction. Yeah? And so far here, we just look at what happens at this point or that point in terms of local environmental conditions. But you said earlier, well, for an animal that shows home-ranging behavior, for those, there's something else that determines whether it's there or there. And that is, there is something like home-ranging, there's something like a central tendency. And when we can integrate that in our model, and that helps a lot with this question of what area do I need to integrate over? So the idea was, here this is our initial function. We just say the degree to which we find the animal here is a function of the local environment. But now the idea was we take into account that there's a center of the home range somewhere, let's say here, and the probability to find it here, here, or here is related to the squared distance from this point. Yeah, so this point here is less attractive, or there's a smaller chance to find the species, not because the local environment is poor, but it is too far away from its home range. So there are two types of factors determining what is going on, where we find the species: the local environment and how far it is from its home range center.
So in this case, the range distribution is specific to the individual because we are just using the individual. If we were to have several individuals, we will have the range distribution for the population, for example. Or it will, because every individual will need its own range distribution.
Yes, every individual has its own range distribution because every individual has its own home range center. And it might also have its own size of the home range, so its own tendency to, the strength by which it is attracted to this center.
So it will always be specific to the individuals that we have the information.
When we do the analysis, we first do it by individual, and then you can generalize from there.
Okay.
So in the code example later on, we will focus on one individual, but there is, and that's already uploaded, an example for how you can work with multiple individuals. Yeah, but that's a very good point. So but it makes sense that when you want to predict the range distribution for a given animal, that you have to take into account what the home ranging behavior of that particular animal.
So you said that the around the center of the distribution, it's a function of distance, that how active the animal is or something, like where we'll find. But there is a asymmetry in the points around the center. Like the more points towards one side, lesser, it's scattered in the lower side. Does this formula also take into account that the utilization might not be a straight, a circular distribution around the center of the home range?
It's a crude description of this central tendency. So it's true that a particular individual will not exactly follow this description. But there's the reason why in the RSF fit and in other cases we use this description is that it's very hard to estimate at the same time the impact of the environment and other factors that make the central tendency if you don't restrict this function to be a very simple one. So it's difficult to estimate the two at the same time. But in a way, what you are hinting at is something that we can do once we have our model that is based only on the environment and the simple home ranging. We can fuse that with the AKDE approach, yeah? To get
Exactly what I
something that
said.
is, on the one hand, using the strength of AKDE, that you take really the positions, and you now infuse what we learned about how the animal used the environment. And that should give us then a fairly accurate description of the range distribution.
Sorry, is it possible, let's imagine that we have our environmental parameters, but then not considering the home range of that individual, but home ranges of other individuals. Like, for example, again, I take about my example. I have a male lion, and this one is covering, let's say, subgroups of females. And I feel that his home range behavior will be affected almost like an environmental parameter by the home ranges of the other females, because he will go there. Is there any, so should I use in that case, can I change with the home range of the other females?
Essentially, you described what you could do. I mean, you said, well, there's kind of a resource, the females around, and you make a map of that. And then that's, from the point of view of the statistics here, it's the same thing as a map of food resources or altitude.
Okay, thank you.
So this year I had promised someone some code to do that in a more precise way, where you start with the initial estimate of the other home range areas that you're interacting with. You run the resource selection functions, and then you improve those home range estimates, and then you keep iterating until you converge. And so you end up with this home range interaction model. I was supposed to have them code already by now, so I'm running a little late. But that's something that's coming fairly soon. But you can do it now, almost as good as the iteration, just by putting in initial estimates of the home ranges in a layer, just like Björn said.
I'm a little bit confused. So you do the habitat selection, you incorporate this home range term, and then you incorporate that with the AKDE?
The AKDE that I was getting way ahead of ours. So forget about the AKDE. This was just you can do even more fancy things. Right now, all we do is we have in our model, a normal RSF, we include elevation. And we include 3 more layers to do this. Because I formulated it here so that it's a bit more perhaps intuitive to understand what is going on, as saying we calculate for each point in the landscape, I calculate the distance to the home range center. I square it, and I then have a parameter that I have to estimate for how strongly then this point is disfavored relative to a point that is closer by. Okay? And the cool thing is that this model, which sounds complicated to integrate here, you can actually calculate spatial layers that you treat as habitat layers, that you stick in your model, that will do this. Yeah?
Okay.
So, this could be a nice exercise during the coffee break, that you just multiply this and then organize the terms. And what you will find is that to estimate all these parameters, because we need to have the home range center in terms of x coordinates, in terms of y coordinates, and in terms of this attraction, that we can integrate this by having just in our model a layer that is the x coordinate, of a cell, another layer with the y-coordinate of the cell, and a third layer that is the x-coordinate squared plus the y-coordinate squared. So we just create 3 more layers that contain the coordinate values, and with that we can estimate the home ranging. Yeah? And that was Chris' fantastic idea, to include the home ranging and how we can do this. Yeah?
I have just one comment. Those coordinates have to be always projected, right?
Oh, yes, absolutely. At least when yes, but that doesn't mean in RSF fit you don't have to throw in, but that's Chris doing. You don't have to throw in rasters that are already projected. You have to do this in the step selection functions later on because that's not Chris who wrote it. So there are a few things that are taken care of for you. But in RSF fit, you don't even have to worry about this, but this is what happens underneath, yes. So, and in a way, one can think of this home ranging as that's our model of availability. Yeah, earlier we had this question, or do you take this area or do you take a bigger area? Well, if you include this home ranging, then it's not so important anymore how big you choose this area. It has to be big enough to include the home range, yes. But if you make it bigger or even bigger, it's not so important typically because the values over here will have anyway a very, 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 very low probability of being chosen by the animal because they are too far away from the home range center. So that is one of the beauties of including a model of availability or a model of attraction to a certain point in the landscape when doing resource selection functions. Yeah. So one of these scale questions in a way is taken into account. So now we have a model and we have parameters. Now we need to do statistics. And that means we have to write a likelihood that tells us how probable it is to observe our data, these points here, as a function of these parameters. So we'll now do a bit the stats part. And then we come back to the concept of use versus availability. Yeah, just that you have a bit of something to hang on to if you want to mentally skip this part now. So this is our basic function that tells us what's the probability to finding the animal, let's say, in a grid cell, anywhere in the landscape. And now we have the observed buffalo Scylla in n locations. So we have n GPS points, okay? And now we want to calculate how probable it is to observe these n locations, given that we have n, yeah? But where they are, with such a model. And the cool thing is, if you just look at the likelihood, you would have for each point, observed point, so used point. You calculate this thing, and if the points are independent, we know they are not, but assuming they were, then we would just have to multiply these probabilities with each other to get the likelihood. Typically in stats, we look at not at the likelihood, but at the log likelihood, and then this product becomes a sum. Okay? So we sum over all individual locations the logarithm of our local intensity, and then we divide by this integral, and this integral is the same for each of the points. So we just calculate it once, and then take it n times. So this is the likelihood if the locations are independent. And we discussed this, that for Scylla, I think we come down to about 18 or 20 independent locations when we say the positions have to be independent. So we don't have a lot there effectively. So we would be pretty wrong if we used our 3,000 points there and claimed they were independent. So what can we do? As I said, the RSF in general assumed that the successive positions are independent. And the cool thing now with RSF fit that we can take this into account. And we just discussed, we have an effective sample size of about 20 out of our 3,500 points. And one thing that we could have done traditionally, you just thin it. Yeah? You take one position, then you wait until the animal has crossed the home range, you take that position, then you throw away the others, and then you take again one. This means you give weight 1 to the first observation, 0 weight to all the others until you again give weight to one position. And the idea now is, well, instead of doing 1, 0, 0, 0, 0, 1, you do 1 divided by whatever it is, 100. So you do this to each point. So use all the points, but each get the weight of 100th. And thereby you don't throw away points, yeah, because you have them. It's just you can't treat them as if they were contributing a full new position. So to come back to this semivariogram that we had seen, here's a time lag in days, and here the semivariance, and the time that it takes for the buffaloes to cross the home range is about 7 days. And this is the point that we need to, in a way, thin to, at least mentally, to get independent points in the RSF analysis. And I've already put in here the line that we later on need for the SSF. Because there we don't need the points, the locations to be independent, but the velocities. And that happens already here at about 3 hours. So we can use a whole lot more data at full weight than here for the RSF. So how do we now integrate the weights in the equations? I put that here. So this is what we had so far. And now we say, well, each observation here doesn't get a weight of 1, but gets a weight such that the sum of the weights corresponds to our effective sample size. Effective sample size was 18. And if we have the points spaced equally in time, then they get all the same weight. But RSF fit can also take into account the case if you have a very irregular schedule, so you have many points close by, then these, say, 3 points that are close by get essentially together the same weight as 1 point that is further away. So this is what RSF fit will do for you. It will calculate what's the original contribution of a given point. Yes?
Sorry, can we go to the previous slide really quick? Really quickly. And this might be apparent to other people, but not me. So if you're trying to do an RSF for a bunch of individuals, my first question is, do you need to do the variogram and kind of estimate that effective sample size for each individual? Or can you kind of have like a rule of thumb if you're trying to do a bunch of individuals?
What we're doing in practice, well, you do this per individual.
Okay.
And then you do your RSF. And then if you're then interested in what happens at the sort of like in a mixed effect models, so what happens at the more general level, then there is a function mean in RSF fit that will then take the individual fitted RSS for all the individuals and weight them accordingly to the uncertainties in the parameters to give you one estimate for the population level model, and we'll also calculate then the variances in the. So when you have a mixed model, you not only have then a model of, say, how the animals react to elevation, but also how that differs between individuals, so that you get a variance on that. And you do the same thing with another habitat, say NDVI, and then you have also covariances between these spreads around this. And Chris has implemented a way of coming up with a model that contains only those parameters that can be well estimated.
Cool, thank you.
But the idea is you start per individual and then you do smart things afterwards. Yeah, here I always focus first on one individual because things get way more complicated in several aspects with several individuals. But it's good to immediately think about the big picture. Yeah. So, this was just the point. Nothing in a way, nothing much happens from there to there. But it's important what is happening is that we give a weight to these observations. And this has, in practice, quite strong consequences for the p-values that you get for your predictors. Because your likelihood then, or your log likelihood, gets a lot smaller if these weights are, say, 1%. Yeah, if they're 0.001, and if you multiply everything with 0.001, then your log likelihood is smaller. And if you then have if you add another parameter, the likelihood of this new model with two parameters will be not that different to the first one. Does that make sense? Compared to one where you have full weights. And that means that when you look at an AIC, there's a large chance that the AIC will tell you just keep the simpler model. Yeah. So now I started with this vision of thinking of RSF as something that predicts probability distributions, where the animal will be, or where we can expect it to find. When you talk about, with ecologists about resource selection functions or selection in general, they rather think in this use availability paradigm. And I just want to make now the link between this perspective of spatial probability and resource selection in a classic perspective of use versus availability. Okay? So what I've shown here is the distribution of elevation. On the one hand, in this whole area, this is the blue area, and that's the histogram here. So most pixels are about 250 elevation, but it goes down from 100 up to, say, 450. That's the blue histogram. And I contrast that with the elevation at the points where we observed the animal. That's the red histogram here. We've seen it yesterday with box plots, yeah, with wind speeds. And this is now the same thing as histogram, so that it's a bit more detailed. So how would you interpret this in terms of what the animal likes or doesn't like?
So the animal is selecting for elevations from around 200 to 260 or something.
Yeah.
Yeah. So it's like using more than it's available.
Yeah, so whenever we see the red bar is higher than the blue bar, we say it's selecting that. And conversely, here,
Yeah.
it's avoiding that. Yeah, so whenever use is higher than availability, it's selected positively or it's avoided. So that's the classic perspective. So now we can, I'll add some terminology. So I call this histogram here for elevation at the used site, I call that the frequency distribution of habit. So that's the used distribution. Yeah. And this is, the blue is the available. Yeah? And we can, now here's a histogram, but you could think of this as really a density distribution. Yeah? So these bars, they add up to 1. And you have used versus availability. And then to put what we just said, that when used is higher than availability, then it's selected for, and otherwise it's avoided. We can plot this like this. So here I have again the elevation, and for each of our bars, our histogram bars, I plotted the height of the used bar divided by the height of the available bar. Yeah. And then I get this. And here I put the 1. So this is no selection. This is use equals availability. And as you said, we have selection for it in this altitude range, and we have selection against it in this range. And this is sort of what we want to describe with our statistical model as this curve is what we want to describe. Yeah? We are looking for the curve that describes this use availability ratio as a function of the environment. So what curve would you perhaps fit to this? Or would you use something that is purely linear? Something quadratic, right? So something that has an optimum, more general. And so this is what I put there. So this is now an RSF model that I fitted to the data. And that's the green thing, which is not too bad compared to what we observe. And in our statistical model, I just put in a quadratic function of elevation. So it's elevation as one predictor, and the squared of elevation was the second one. And that allows me to get an optimum elevation selected by the animal. Okay. Here in this part, I did not include this home ranging. I just did the classic thing, only comparing use versus availability. And then when we plot this in space, we get this. Yeah? So it's here now, green means this is good habitat, and white means this is poor habitat. And coming back to what you said earlier, what's obviously still missing here? I mean, we don't take so far the river into account. Yeah?
It actually looks like, if I just look quickly at the map like that, it looks a problem of slopes more than altitude.
Now we're getting into the ecological thinking, right?
Yeah,
so
okay.
what is happening here? Yes, here there's something. Here you have strong slopes, and then perhaps often it's not altitude per se that animals care about.
It really looks like physical barriers of accessing the higher parts, because as soon as there is a lower slope, you can see it maybe starting to go, and the river can actually act as a slope, a negative slope.
Yeah. So here it's steep from the point of view of the buffalo, so it doesn't go up there. And here, yeah, we have a missing variable in a way, the fact that there's a river. And you could, to integrate this, you have now several options. I mean, if you see this and you know this, you can just say, all this area is NA. So I exclude this from my available area. So I don't integrate over this because I know the probability that the animal is there is 0, and I fix this because I have this knowledge. If you have animals that are within a fence, then it makes sense to say, well, I'm only looking what happens inside the fence, and the rest is off limits. So they even, I mean, I just said, well, if once we integrate the home ranging, we get rid of this question of scale. We don't get completely rid of it because there might be harsh barriers that we need to take into account. In theory, you could also have a layer that says this side of the river or that side of the river, and then you can estimate what's the probability that the animal goes to the other side of the river. In a case where it's never crossing, it's not so interesting. But it could be interesting, in particular later on for step selection functions, when you have a road and you want to see what's the probability that it crosses a road.
Bjorn, I have a question.
Yes.
So just kind of thinking about this and kind of going back to, including the home ranging element into the model, does that eliminate the need, like, I feel like in some instances in the past, sometimes people have kind of created a, maybe an MCP around, the points to kind of calculate what's available to that individual. Does that eliminate the need to do something like that because it does take into account that central point? Okay.
Because you could also, when you either do an MCP or do an AKDE, and based on that you calculate, say, the 99% home range and say that's where it is. And that has a bit the idea that outside of this available area, it is completely unavailable, and inside it is completely available. Yeah, so in a way you put a priori, or outside the fitting process of the RSF fit, you put a model of availability. You say here it's not at all available and here it is fully available. Yeah, so you draw the boundaries. You might draw the boundaries based on the data, but it is something that the RSF later on doesn't see anymore. So it also cannot, the parameter estimates of the RSF cannot reflect the uncertainty in this because it's not certain that the boundary goes here and not there. In the case of the river, I would say, well, that's certain, right? I mean, that's easy. But if you have, here this is a decision that you can, in a way, algorithmically, you can solve this by saying I use the AKDE, but still, then the RSF doesn't know that you pick this or that level of
like a
boundary.
So
yeah,
sorry, go ahead.
And by integrating this model of availability, this home ranging, the model or all the parameters, for example, the section of elevation, they depend a bit on this availability, and this is then the uncertainty in deciding the availability is also reflected in the uncertainty of the elevation.
Okay, so it's kind of just good practice to include that in the model. Thank you.
The whole thing of this RSF as we design it, it is made for animals that show home ranging behavior. If it doesn't show home ranging behavior, or you work at very different scales, then you have to think about how to include the availability model. Mm-hmm. But it's always good practice to do the weighting. That is always important. And then the home ranging is typically a good idea if you have a home ranging animal.
I think you kind of just answered what I was asking, but what if we wanted to look at the habitat's influence, say, like if animal that went on a foray outside of their home range? Would we include like the whole entire area between their home range and kind of where they traveled?
Yeah, I mean, if it's in general an animal that is a range resident, then in terms of the whole area that you take it at least as big as all the points that you have, and you make sure that it also, and you can get guided for that by the AKDA estimate, that it's big relative to the full home range, which and then you would still include this home ranging factor, but you would include then in a way automatically. So if this was here, not ending here, but going over there, you would include this as part as well.
Even if, say, that area wasn't particularly included in the home range estimate? You know, if they like went there, but it's not exactly included.
No,
like,
I would include it. I mean, the question is at some point if you think there are really different behavioral modes, then I could imagine that you say I make a model for the range resident animal while it is range resident, and then there is other periods where it's doing other things, and I might be interested in what it is doing there. I mean, I would expect that if you have something that is just one exploration that happens once, that it won't affect the estimates very much because of the home ranging factor. It'll get very low probabilities to go there, so the model won't take very much the local environmental conditions into account. I don't know, Chris, whether you have another opinion on this. I mean, the question was, to what extent, if you have now something that makes excursions, should we just leave it as is? I mean, that would in a first approach that's what I would do.
Yeah, I agree with you. It's either that the home range is a heavy-tailed distribution, so these occasional forays and sallies exist, in which case you leave them in, and you just try to model the heavy-tailed distribution as best you can, or it's a different behavior, and you segment based on behaviors. And when you do that, if it's just one, I mean, statistically, there's absolutely no way you can distinguish between two models when n equals 1. So you just have to use your own biological judgment.
Okay, I have one more complicated slide that tries to summarize this part on the habitat, and then I have a few pictures, and then we have break, okay? So that you... So I said we wanted to look at how this use availability paradigm maps to geographic space. And what we've done so far is we've looked at how the use availability paradigm works, okay? And that's what we see in detail here. This was this was the used histogram. Yeah, this was the red for histogram here. And we say the red histogram is proportional to the blue histogram, yeah, by weighting the blue histogram with our selection. Yeah, this was the curve. Yeah. So you go from what is available to what is used by giving weights to the available according to its selection. So if it's available but it doesn't use it, it doesn't like it, it's not going to use it much. And even if it likes it a lot and it's almost not available, it's also not going to be used very much. And as always, because we want this to be a distribution, this is a distribution, and if we do some funny things with that distribution, we have to normalize it again. So this is sort of the used availability paradigm. We got our blue curve, red curve, and our selection. And now coming back here to our geographic space model that we started with. And here now I say, what's the probability that I'm at this point S? And just to confuse you, I changed the terminology. So this was earlier, this was P of S given lambda, if you remember. And then you had here the lambda. This is our lambda. And this is the integration over lambda. Okay? And what we now have here is we have the very same selection here, the W, that we have here. So that's the same. That's where the preference for a certain resource, the resource selection is the same in both. Yeah? Here it's directly the X, and here we say, well, to go to this point, we look at the resource level at this point S. Yeah, so this, in both cases, would be elevation. And then here we have this availability of space, which is classically, you would assume, that's what I did in the earlier analysis, that every pixel in my sublandscape is equally available. And when you do this, then essentially what we see, we have the same weighting factor of either an environment or space that we use to get our spatial distribution or our environmental distribution. So another way of thinking about this is we often focus on this because this is what we tend to be interested in, how the animal selects for certain environmental conditions. But in order to describe this, we always have to have some idea of what space is available. And one way of dealing with this problem, the classic way, is you decide what part of the map you call available. Everything else is not available, everything else is inside. Or the idea is to include here some home ranging parameter, which has a bit the effect of saying, well, this near the center, this is very much available, and this stuff over there, it's not, it's much less available. So this is how these things match together. So now, last element before the break is now, how do these things look like? This is now the model of the AKDE for Scylla. We've done this before. And here's the color scale. So this is not used. This is very much used. The values in the landscape sum up to 1 in all cases, and it's the same color scale. So here we have something that is a bit diffuse. There's a blob. And here to the right, we have the output of a model that uses elevation. And I think it's only using elevation. Yeah, it's not elevation square. So that's why it's quite attracted here to the lower areas. And these are the points. And they are good and bad things for both, right? I mean, here, what is nice is you see this little mountain range is excluded, so that seems good. But then here, this model would say whether they shouldn't be there, and they are there, and the AKDE gets that much better. And then this is now the combination of the AKDE and the RSF fit. So in practice, you refit the AKDE and give it as an argument the output of the model. And now you get sort of the AKDE better describe this part down here, but you keep these areas that are not very much used there. Yes?
Hi, is this potentially a way of comparing, let's say, habitat quality? So there's the idea that maybe an animal might have a bigger home range because the quality of the habitat that's available to it might not have resources it needs, so it needs to expand the amount of space it takes up to find the resources. So for example, in my case, I have goshawks who use forest, but the habitat's very fragmented. So in my head, it makes sense they may have a bigger range distribution if the resources that they're selecting aren't as bountiful, and then if they have lots of forest, they have a smaller home range. Is that a way of potentially comparing sort of resource use to how much they have to range in order to get enough resources?
I mean, to me, this is a problem that goes a bit beyond what the RSF directly does, because the RSF, in a way, says, given that the animal is around here, what is it selecting within its home range? And you.
I suppose it's more about comparing individuals.
Yes.
Idea that.
I mean, to me, the basic type of model for what you're interested in, I would say, well, my response variable is not where it is, but how big the home range is. So that could be sort of the response variable. And then you describe it by what is inside the home range, or what is at a given scale. And then you could use perhaps the RSF to qualify the sort of the for each pixel in the landscape, its quality, and then you calculate within a home range what's the average quality, and then you say, well, this is explaining or not the home range size. I mean, that's doable, but it's in a way you in the first step do your analyses of selection, and then you use that as a way to have a common way of describing the landscape, not in the original variables like forest, non-forest, but in terms of more of resources or degrees of selection. And then you're interested in whether in a way the average value of resource explains the size of the home range. Yeah. So yes. I mean, we did this, years ago, that we were interested in, within a home range, whether the degree of structure, so fragmentation, affects the home range size. So we did that for roe deer. Red deer. So yes, I mean, that's how we did it at the time. So we didn't really go we didn't go via selection first, but that would be an option to give perhaps a bit more meaning to the landscape description that you use.
Sorry, I have a question about the previous thing. We were talking about the use availability paradigm, and I'm not so sure I got the point of the comparison with the RSF. Are we saying that they're very similar and doing the same thing, or that they are different?
They're the same thing. It's just there are different ways of looking at it.
Okay.
So in one case, you're mostly so in a way, what the stuff that we estimate is this W thing, yeah. So that was and you see that the W thing is the W thing is the same in both cases. Perhaps it's not so obvious given the terminology I use, but sort of the weight, sort of whether the animal prefers this value of elevation or that value of elevation, or this amount of biomass or that amount of biomass. That is what we want to estimate, and we estimate it in both. Well, it's the same model. It's just that in one case we use it to say where in space the animal is. In the other case we say where in environmental space the animal is. And what is written here, which is a bit subtle, is that the availability of a certain habitat value is not necessarily that obvious, because it's easy to calculate if you have an area where you say, geographically speaking, it's available or not, because then you just extract the values of your raster and you have an histogram. But if you say, well, this area is available, this is a little less available. So if the degrees of availability differ, then it's a bit more complicated to calculate the availability of a habitat. So that's where these things then become more, but where they are really entwined, and where it's important to see that they can be entwined. But basically, we want to estimate in the first step this, and what we've now seen, that was the Chris idea, well, actually, we can also estimate availability.
Thank you.
With that, I suggest we make a break. I don't know, is now break time anyway, or did we pass it, whatever?
Breaks whenever you feel like, and say.
I feel like a break. And then we come back and then we do the exercises with this so that we see how this actually works. And then after that, we do the SSF stuff.
I wanted to say one thing. We wanted to apologize for the hustle of the microphones. That's the question, but it's really important because all the discussion is really important. It's like really important also for everybody watching the videos to understand, and because they probably have equal questions that you might have. And the reason why we're doing these videos is because we only have the space, and there are many people that want to come, so we want to make the material available to as many people as we can. So just so you understand why we go through the hustle. Thank you.
One thing, guys, I don't know if everybody has sent information about the food that they want that we send in the WhatsApp group, but I'm about to send those to Regina. If anybody else needs something, put it on the form right now. Otherwise,